Ever since we first looked up at the sky, we've wondered about light. Is it just there, instantaneous? Or is it moving at some crazy, finite speed? Well, for centuries, scientists have been chasing this ghost, trying to clock the universe's ultimate speed limit. And that is the story we're diving into.
So here's the number: 299,792,458 meters per second. But, this isn't just some ridiculously fast speed. It is a fundamental constant of our universe. It's one of the pillars that Einstein's theory of relativity is built on. It's basically the law. Nothing with mass can go faster. Period.
But getting to that exact number, wow, that was not easy. It's a story full of failures, moments of pure astronomical genius, and some really, really clever mechanical gadgets. This is the story of a centuries-long scientific adventure, all to pin down one of the most important numbers in all of physics. All right, so where did this whole chase begin? Let's jump in. Our journey kicks off back in the 17th century with one of the biggest names in science, who came up with an experiment that was, well, brilliantly simple, but also totally doomed from the start. So this was Galileo's big idea. He and an assistant would stand on two different hills, a few kilometers apart. Galileo uncovers his lantern. The second his assistant sees that light, he uncovers his own. All Galileo has to do is time the delay. Simple, right? Well, there was one tiny problem. Light travels that distance in microseconds. Human reaction time, we're talking tenths of a second. So Galileo couldn't really measure anything, but he did correctly figure out that light must be, in his words, instantaneous or extraordinarily rapid. So the first real proof that light has a finite speed didn't come from here on Earth at all. It came from looking at the heavens. In 1676, a Danish astronomer named Ole Romer was watching the eclipses of Jupiter's moon, Io, and he noticed something weird. The eclipses seemed to happen later when Earth was farther away from Jupiter. And then it clicked. The delay wasn't the moon being late. It was the extra time it took for the light from that eclipse to travel across the huge diameter of Earth's orbit to reach his telescope. The entire solar system basically became his laboratory. How cool is that? Just look at these dates for a second. More than 200 years, 2 centuries passed between Galileo's lantern attempt and the very first successful measurement here on Earth. That huge gap tells you everything you need to know about how monumental this challenge really was. It was going to take a completely new way of thinking to solve it. Okay, let's fast forward to 1849. After all that time looking up at the stars, a French physicist named Armand Fizeau finally figured out a way to build a machine that could actually catch a beam of light right here on our planet. Now, Fizeau's setup, it looks a little complicated, I know, but the core idea is just pure genius. It's got a light source, a mirror placed a long, long way away, and then the star of the show, a rapidly spinning toothed wheel. Okay, so here's how this ingenious thing worked. A beam of light shines out through a gap between the wheel's teeth. It travels all the way to that distant mirror and then reflects straight back. Now, if you spin the wheel at just the right speed, by the time the light gets back, a tooth has moved into the way and it blocks your view. It's like a super fast shutter. So if you know how fast the wheel is spinning and you know the distance to the mirror, you can calculate the speed of light. Absolutely brilliant. And when I say the distance wasn't trivial, I mean it. In his experiment, that mirror was placed on a hilltop, a staggering 8.6 kilometers away. That's over 5 miles. The beam of light had to make a round trip of more than 17 kilometers just to give that little wheel enough time to rotate. So, Fizeau had cracked the code. He proved it could be done. His result was only about 5% off the true value, which is pretty amazing. But now the race was on for precision. The next generation of physicists took his brilliant idea and just ran with it, refining it to an incredible degree. And the very next big leap forward came from Leon Foucault. He had this realization that the kind of clunky, imprecise toothed wheel could be replaced with something way more elegant, a tiny, rapidly spinning mirror. And that one change, it was a total game changer. It allowed the entire experiment to be brought from the hilltops into a controlled laboratory. So in Foucault's setup, light bounces off this rotating mirror, travels to a fixed mirror, and comes back.
But in that tiny amount of time it takes for the round trip, the central mirror has rotated just a tiny bit. And because of that, the returning light beam gets deflected by a very small but crucially measurable angle. And by measuring that tiny little shift, Foucault could calculate the speed of light with even greater accuracy.
And that brings us to the guy who basically made this quest his entire life's work, Albert A. Michelson. This man was obsessed with getting the most precise measurement possible, and he spent decades just perfecting this rotating mirror method. Nicholson's genius was really in the details. For one, he used a long, evacuated tube to get rid of the distorting effects of air. And then he replaced the single rotating mirror with a perfectly machined, multi-sided one. Think like an octagon. Using more faces like that gave him a much more stable and bright return signal, which dramatically improved the precision of his measurements. So, after centuries of chasing light from hilltops to high-tech labs, scientists had finally cornered it with just astonishing precision. But the end of this story isn't just about getting a number right. It's a really profound shift in how we think about the universe itself. And here it is again. Thanks to the work of Michelson and so many others who came after him, using things like lasers and atomic clocks, we absolutely pinned down this value. It became one of the most precisely known quantities in all of science. So precisely known, in fact, that something really, really remarkable happened. We stopped measuring it. That's right. In 1983, the scientific community basically flipped the whole concept on its head. The speed of light is now an exact, defined value. It's not something we measure anymore. Instead, we use this fundamental constant to define what a meter is. A meter is, officially, the distance light travels in this ridiculously tiny fraction of a second. This quote just captures that incredible shift perfectly. We are now so confident in the speed of light that we use it as our ultimate ruler. The quest to measure c was so successful that it ended by becoming the very definition of how we measure space itself. And so, the journey that kicked off with two guys and two lanterns on a hill ended by literally redefining distance itself. It's just an amazing testament to centuries of scientific curiosity and ingenuity. And it really makes you wonder, right? With the speed of light now a fixed landmark in our universe, what's the next fundamental constant humanity is going to chase?